All right, so this mini lecture is going to look at energy in simple harmonic motion. And we actually already have all the tools that we need to look at energy with simple harmonic motion because we have this background in conservation of energy in mechanical systems. So I encourage you, if you haven't checked those videos out yet, watch those videos. It goes through really the premise of conservation of energy, and we're going to use that to analyze energy in simple harmonic motion. So it'd be really good to have that background. Now, as a quick recap of that, conservation of energy basically tells us that assuming no non-conservative forces acting, where we would have energy loss, it's of course conserved in the larger system, but through heat or sound or heat and sound, we'll go with that, that the mechanical energy of the system at one point in time is the same at all points in time. So energy, the total energy at one point in time has to equal the total energy at another point in time. Now, we're going to stick in our simple harmonic motion idea the theme of an object on a spring. So let's imagine that we have an object on a spring and it's oscillating on a horizontal surface, frictionless horizontal surface. And so if this is its natural position and that object is stretched to a new position with some amplitude A, that restoring force is going to pull that, on release, pull that object back and go to a compressed position. That was not good symmetry, so let's make this a little shorter so I have good symmetry. All right, and it's going to oscillate back and forth around this natural or equilibrium position. What type of energy, mechanical energy, do we have in this system? Well, we have energy of motion. Remember, that was our kinetic energy. And we have potential energy. I'm going to use PE for my description of potential energy. In this system, that potential energy is made up of the energy in the spring. All right, and in all cases, energy is going to be conserved, so the kinetic energy at some later point in time has to equal the potential energy at that later point, the total energy at that later point in time has to equal the total energy in the earlier point in time, and again, made up of potentially kinetic and potential energy. Now, where does this, can we utilize some information about simple harmonic motion to understand the total energy? So what is the total energy of the system? And how can we determine that with our understanding of simple harmonic motion? Well, let's just talk conceptually about what's happening here, right? I pull the spring, and when I pull it, and I stop and get ready to release it, right at that instant of release, I don't have any motion. So my total energy is made up of the total potential energy that exists in the system. Well, what's that potential energy due to? Well, that's due to the spring. And we know that the potential energy of a spring is given by 1/2 K, where K is our spring constant, times the position, how long it's stretched, how much it's stretched, times that squared. Well, in my description of simple harmonic motion, how much it's stretched is what we refer to as the amplitude. So the total energy of the system is the same as 1/2 K times the amplitude squared. The total energy of a simple harmonic oscillator on a spring is given by 1/2 K times the amplitude squared. That's pretty useful information to have. Now, is that the only information we have? Well, let's keep going through this motion. As I stretch the spring and I release it, it starts to move back in the opposite direction. So I lose potential energy because the spring is compressed, and I start to increase my motion. I have motion now, so I increase my kinetic energy. As it approaches the equilibrium position, what's right at that position? Is the spring stretched? No. So right at this position, there's no potential energy of the spring, which means all of my energy is wrapped up in kinetic energy. And so the total energy of the system is also defined by the kinetic energy when it's moving the fastest, which is 1/2 mv max squared. Now we know in a simple harmonic oscillator that that's information we have based on frequency and amplitude. So remember, our maximum velocity in a simple harmonic oscillator is 2 pi times the frequency times the amplitude. So again, we have information about the energy, the total energy of the system, based solely on the properties of the simple harmonic oscillator. What its K value is would allow us to get the potential energy right off the bat, and the amplitude would allow us to get that total energy. If we know the frequency, or if we know the mass and the K value, we can get the frequency. So we can use our equations that guide our simple harmonic motion to determine the total energy of the system. Once we know the total energy of the system, we can determine various aspects of a problem that might look at where the energy is in terms of its kinetic and potential energy at any other point in time, not necessarily at the maximum potential energy or the maximum kinetic energy. All right, so really kind of back to that idea of energy conservation. It gives us the tools to have some relationships that tell us the total energy of the system for a simple harmonic oscillator. Either one of these will give us that information. All right. There's another video that goes through a practice problem like this. I encourage you to kind of look at how we use this information. This is just to introduce you to the ideas. Good job.